In this video, we are going to learn the difference between first and second law of thermodynamics, and with a brief example I will try to explain why second law of thermodynamics is necessary and the need of heat engine and working fluid. So I will take a simple example. Let us take a ball of mass m, and we want to throw this ball to a certain height h. Let this position be called as position 1. Initial position I am calling it as 1, and final position is suppose 2. So this is our initial position and this is our final position, and our desired goal is to throw this ball to a height h. So if we throw this ball with sufficient kinetic energy, it will move to position 2. We all know that. And if we calculate the value, suppose the mass of the ball is 1 kg and height, or the difference between the height of 1 and 2 is 1 meter, and taking 1 as our datum, so initial potential energy will be 0 and final potential energy will be mgh. If we take the value of g as 10 meter per second square, so the required kinetic energy to move the ball from position 1 to 2 will be equal to mgh. That is the difference in half mv2 square minus half mv1 square equals to mgh. So the required kinetic energy of the ball is 10 joule, putting the numerical value as mass of ball as 1 and g as 10 and height as 1. So the required kinetic energy is 10 joule. This we all know, and it is a very simple example. Now if we want to move this ball from position 1 to 2 by using different form of energy, initially it was kinetic energy, now we are using different form of energy. In this case I am using thermal energy or heat transfer to move this ball from position 1 to 2. Now suppose we start heating this ball. What will happen? Its temperature will increase, but this ball will not move. The previous calculated value was, suppose 10 joule of kinetic energy was required to move the ball from position 1 to 2, but in this case it is not going to happen. If we transfer heat in the form of 10 joule, so that 10 joule will not be sufficient to move this ball from position 1 to 2. If we increase the temperature, what will happen? This ball will start glowing, it will increase its temperature, then it will become red hot. Everything is going to happen, but as far as its motion is concerned, it is not going to move. It will not move an inch. If we increase the temperature further, it will melt, but it will remain at its same original position. So our desired goal was to move from position 1 to 2. So in this case, when we are transferring heat in the energy in the form of heat, in this case we are not achieving our desired goal. Earlier, with the help of kinetic energy, we were achieving our desired purpose, that is the ball was thrown from position 1 to 2, or it was moved from position 1 to 2. But when we transfer heat to this ball, this is not going to move. So here this first law of thermodynamics, which says that delta Q equals to delta U plus W, is not going to explain why this is not happening. First law of thermodynamics simply says that if we transfer heat to this ball, part of heat will be utilized in the form of internal energy and part of it will be in the form of work. In this case there is no work, so all the heat or the heat transfer that is supplied to this ball will be utilized to increase its internal energy. However, we are not achieving our desired purpose. To achieve our desired purpose, we do something different. We take a long cylinder with a movable piston. This is our cylinder, this is cylinder, and this is our movable piston, the horizontal one, and on this we keep this ball of mass 1 kg. Now if we heat this ball, now what will happen? This ball will increase the temperature of the gases which are trapped in this piston and cylinder, where we are calling this the gas that we are using. In fact, we can use any fluid and we call it working fluid. So this is our working fluid, which will get heated when we supply heat to this system. And when this working fluid is heated, it will expand, and because of the expansion it will push the piston. This is piston. It will push the piston upward, and so the ball will move from its initial position to final position, and we can say that our desired purpose is achieved. So there are two things that we are using here. One is the piston cylinder device, which is in general called the heat engine. So right now I am calling this piston cylinder device as a heat engine, and this is heat engine, and in which there is a working fluid. In this case I am using air as a working fluid. This working fluid expands, and the desired purpose of moving the ball from position 1 to 2, or to lifting the ball to a height h, is achieved. Now coming to this first law of thermodynamics. This is our first law of thermodynamics, Q equals to delta U plus delta W. Now when we are heating this working fluid, its temperature will increase from initial temperature to final temperature, and we can say that delta U is mass into specific heat into change in or rise in temperature, or we can take this M as number of moles. So in this case mg will, mass of gas will be in fact number of moles of gas into specific heat. In this particular case specific heat will be Cp, constant pressure process, because the pressure remains constant, and then this Tf minus Ti. Now notice that this energy which is used in heating the gas is not utilized during work done. What will happen is that this is in fact treated as waste energy as far as second law of thermodynamics is concerned. Although it is not something that is useless, we are calling just a nomenclature because this energy is not utilized in our, when we are taking heat from the source. Only part of it, that is when we are taking energy Q1 from the source, only part of energy is utilized in work done, and the remaining part, that is Q2, which is used to increase the internal energy of the gas, is not utilized. In fact, it is wasted. I will show how it is wasted. Suppose we want to repeat the process once again. So the piston will move down, the gases will come to its initial state, and when it comes to its initial state, this energy which was gained by the gas to increase its internal energy, that has to be rejected to the environment, and this value is Q2, which is mass into specific heat into the rise in temperature, which was initially risen to final Tf temperature. This energy has to be released in the environment or rejected in the environment, so that the gases moves to its initial state. Now if we again repeat the process, again we will keep one mass of 1 kg or whatever kg we require, and again it will be heated, and the cycle can be continued again once again. So this is my basic explanation of the difference between first law and second law, the requirement of heat engine and working fluid. Now in order for the completeness, I have mentioned this Kelvin-Planck statement. This is second law statement. It states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work, which was shown by my example. By heating the ball directly, we cannot move it. Almost this is what Kelvin-Planck statement says. And second is the heat engine, which I have explained. The first statement is, that is, converting heat to work requires the use of some special devices. which I was trying to show that we cannot move this ball by just simply heating it. We need a device, and that device was, in this my example was piston cylinder device, and that device is known as heat engine. They receive heat from a high temperature source, any solar energy or oil furnace or nuclear reactor, etc. They convert part of this heat to work. Here the work was to lift the ball from position 1 to position 2 or to a height h, and some part of heat is rejected. That is, they reject the remaining waste heat to low temperature sink. In my example, the waste heat was the rise in internal energy of the gas, which was rejected to the environment. So this completes our video. Thank you.